I recently watched a video online talking about why you should solder your automotive high current cables, and it's just pretty wild that someone would suggest that that's, accepted in industry or somehow not a terrible idea. Crimping, there is no question about it in the automotive industry. You crimp your connections because you don't want embrittlement from solder that wicks down the copper, causing failures. And yes, you can add strain relief, you can add recessed, channels that things can ride in, but unless you're potting things in epoxy or building a circuit board, you're still gonna have localized vibration, even if you have, some kind of local constraint, because things with different mass respond differently to external stimuli. No one in the automotive industry, at least the respected automotive industry, uses soldered cables on their things, again, unless they're potted. Like if you had an over molded USB cable, yeah, that's going to be soldered. But a high current cable like this that can handle 150 amps or whatever, that's always going to be crimped. In this video that I watched, the crimps did not look that good. I did see what looked like a professional crimper in that video, but the actual crimp that was shown seemed to be incomplete. And if you look, the crimp in that video was 370 microohms versus their solder was 250 microohms, and then both was 290, which again, that's the one that looked really bad to me. It's weird to me that if solder was better, that doing both would be worse. It seemed like maybe the soldering method was done differently. I don't really have any comment on that. I'm mainly looking at the difference between the crimp and the solder. Because no one's gonna do both. It's kind of weird. Unless you're soldering it after the fact because the crimp is bad. There's a secondary argument made in this video talking about how environmental moisture will cause crimped contacts to fail. And that's just not correct if you have crimped it properly, because you get a cold weld. There's no oxygen in here to oxidize. So the outer copper can oxidize, and of course, in both cases, whether or not you crimp or solder it, you could have oxidation that causes your cable to fail, but it's not going to be in here at this joint, at least not any worse than soldering. So I don't buy that as a valid thing. And of course, the embrittlement you get when that solder wicks down here isn't worth the trade-off. And again, localized mechanical strain relief that's only preventing you from moving slightly is not a solution to prevent the embrittlement from causing fracture, from causing a fatigue failure inside of this copper, wherever that copper ends. So I want to note too, the delta here is actually quite small. It's 120 microohms between crimping and soldering. So soldering in that test was 120 microohms better. But if you look at 150 amps, you're talking about 2.7 watts of additional power in a cable like this. When you're pushing, say, at 150 amps at 240 volts, you're pushing 36,000 watts. So 2.7 watts is nothing, especially compared to the amount of internal heat loss you're going to have from the chemical resistance of the battery cell. So, for example, most sodium cells have much higher, in fact, I think all sodium cells have higher resistance than traction batteries used in lithium hybrids. Certainly in my testing of the sodium cells that I have tested, it's much higher. You're talking about 5 kilowatts or more of internal heat inside of the battery pack. So if you're worried about a 2.7 watt increase on something that you have maybe 10 of, you might have 10 of these connections in a pack to hook up the submodules or whatever. In some cases you might have 4 or 6. One of my products has 10, one of them has 12. But you're talking overall, when you have 10 of these connections, you're talking about, in their test data, 30 watts of extra heat when you have a 5 kilowatt thing that it's connected to generating heat as well. So you're talking about less than 1% of the issue is here versus in the cell itself. So the point is, the claimed benefit of the slightly lower resistance, 120 microohms, is inconsequential compared to the other amount of energy inside of this pack that's being released. So I wanted to show you today my tester that I use on all the cables that I build. The tester shown in the video that I watched, it has much lower current. I'm not saying it's an invalid test, but when you're looking at something that's at 150 amps, in use, and you're testing it with 50 to 100 milliamps, you're not really in the actual range there, and so you get some measurement error. What I'm using instead, again, I have no critique on the test equipment that was used in their test, but I do want to say why mine is better. This is a 100 amp current source. It's actually just a programmable power supply. I have it set to 100 amps. And because I'm testing at between 1,000 and 2,000 times higher current than the tester video that I watched, my voltage measurement has between 1,000 and 2,000 times more accuracy given the same test equipment. Now this fluke meter alone costs more than the entire setup in the test equipment in the video that I watched. So I certainly have more accurate equipment, but again, I'm not faulting the test methodology shown in that other video. I'm just saying that I'm gonna have a lot more resolution here. I'm certainly gonna have a lot more accuracy. I do have a local voltage reference, a 10 volt reference, and this one is spot on. I used it to back calculate the current measurements here, and we are close enough. We were off by 50 milliamps, again, on a 100,000 milliamp application, 100 amp supply here. So I wanted to show you my tester and what it is. I have these two toggles, and our current runs through these bars here, and then we measure the voltage on these tops here. There's basically no current running through this. And the way we can validate that this test fixture works right is you can take a big piece of copper here and you can put it on the test fixture like that, and then put 100 amps through it. You can see we measure a 2 millivolt drop at 100 amps through there. We're only measuring the voltage drop in the copper to in the copper in that case. So what was the value again? Sorry, 2 millivolts. So we're talking about 2 millivolts divided by, 120 micro ohms through this copper plate here. So that's just kind of the test setup showing that it works here. So let's look at this cable that I just, this is a cable I ship, and I test all my cables with it. It's why I have this test fixture. And so what you do is you take your cable here and you clamp it down like that, and you clamp it down like this, and then you hit go, and you see I have an 18 millivolt drop, so 0.018 divided by 100 amps, you see I have 180 micro ohms. And that's going through 2 connections. In the video I watched, we were doing 1 crimp and a short section of wire. I'm doing 2 crimps and a short section of wire, and I'm getting half the measured resistance. So I'm better than soldered. I don't have a soldered thing. I don't solder cables. There's no reason to. It's wild to think that you need to. It's like there's a zero-sum game or something in that other video of like, if you crimp, your resistance will be higher than soldering. And it's like, no, if that's an issue, if you can't handle the extra 2.7 watts due to this delta from their test data, you need to use a thicker terminal. You need to use thicker cabling if that's an issue. It's not, right? Pushing 150 amps intermittently through a 4-gauge wire like this, no problem. You can do that all day long. It's weird. It's wild to see someone speak to the industry and recommending that soldering automotive cables that are going to see vibration is a good thing. It's not, and you should not do it. There's almost no reason why you would need to do it. Look at industry. Look at all of the assemblies out there. Show me a soldered cable that is not then overmolded, cast in epoxy, cast in plastic, to where there is no vibration. There's no separate vibration. Just putting your cable in a channel, it doesn't work because you can still vibrate. Unless that channel is then filled with a resin, you're still gonna have local vibration, and you don't want that embrittlement coming down into your copper. That's why you crimp things. And with cold welding, the resistance between the actual contact surface here and the wire, you're not gonna develop an oxide layer there because there's no oxygen in it. Now, if the whole cable and assembly corrodes, that's a different problem, and it affects soldering equally as much as it would affect a crimp connector. So I just had to get this video out because it's wild to think that someone would claim expertise in something and then release a video that wild. And my only concession is maybe it's around April Fool's, but didn't come across in the video, but it seems unlikely that that's the case, particularly because of all the previous videos showing soldering from this individual. So pretty wild. Just wanted to interject with my own commentary because that's what I do. Thanks for watching.